we present SceNeRFlow, a NeRF-based method for time-consistent 4D reconstruction of general dynamic objects. As input, we take multi-view RGB videos with known camera parameters and background images. We then reconstruct the non-rigid scene in a time-consistent manner. In contrast, almost all prior works on general 4D reconstruction focus on novel view synthesis and neglect long-term correspondences. Other methods, like SceNeRFlow, are time-consistent by design, but only work for small motion. Our method, however, can reconstruct large motions while ensuring time consistency. As we will show later, this leads to a trade-off with novel view quality. We volumetrically encode the geometry sigma and the appearance C in a static canonical model. We construct this canonical model from the multi-view input images from time t=1. To render the model into 2D, we shoot a ray R from camera C into the scene and sample random points on it. To focus on the dynamic foreground, we add the static background image to the end of the ray. We then use NeRF-style volumetric rendering to obtain the ray color. We encourage similarity to the ground truth with a reconstruction loss. In addition, we regularize the geometry. After this construction, we keep the weights of the canonical model fixed. This is crucial to ensure time consistency. We next model the deformations for any later time t. Since we need to handle large motion, we use an online optimization where the deformations at time t are initialized with the deformations from t-1. To stabilize the optimization, we split the deformations into a coarse and a fine component. We regularize the coarse deformations with a strong regularization weight, and the fine deformations only weakly. We first apply the coarse offsets to the points, and then add details with fine deformations. We then query the canonical model at the resulting points and apply volumetric rendering as before. This enables us to use the reconstruction loss with images from time t. Here are the reconstructions obtained by our method. We compare against SceNeRFlow, the main prior work on time-consistent reconstruction with NeRF. Our reconstructions are of high quality, while SceNeRFlow shows artifacts because it does not correctly estimate correspondences for large motions. Next, we evaluate the time consistency of our reconstructions. Here we compare against PREF, which is a NeRF-based method to estimate 3D correspondences. To measure time consistency in 3D, we follow PREF and use estimated 3D human joints as pseudo-ground truth. At test time, we track these joints from the first timestamp until the last. Our method outputs stable correspondences, while PREF and SceNeRFlow show substantial drift over time. Our method design is built around time consistency. Next, we want to get a better sense of the trade-off between time consistency and novel view quality. We thus introduce two variants of our method, SceNeRFlow A and SceNeRFlow AG. The first variant allows the appearance of the canonical model to vary over time. The second one makes both the appearance and the geometry of the canonical model time-varying. Both these variants can thus better overfit to any specific time t. This leads to better novel view synthesis for the dynamic objects. We can see this by looking at the dress, which the variants reconstruct much more accurately. However, these modifications also loosen the correspondences, as we can see by observing that the canonical model changes over time. We next ablate the core components of our method. The online optimization provides strong guidance to the correspondence estimation. Smoothing the deformation field provides plausible initializations for the next timestamp. Furthermore, the coarse deformations make the reconstruction more stable, and the fine deformations add subtle details. Finally, time consistency also makes long-term time-consistent editing straightforward. For example, we can modify the appearance and make the geometry transparent. Thank you for watching.